Hello. So we have a problem here. It says calculate the pH of a 0.1 molar sodium acetate solution. Okay. And you're given the Ka to be equal to be 1.8 times 10 to the power minus 5, the Ka of the acetic acid. You might be wondering, the question is asking about the pH of sodium acetate, but you are given Ka of an acid. Why is it so? You should realize that sodium acetate is a weak base and it comes from acetic acid. So acetic acid is the conjugate base. If you try to neutralize acetic acid with a base, it's going to give you sodium acetate. And you learn those in buffers. So look at the number. Ka of acetic acid is very low. The Ka, by the way, is ionization constant. The lower the ionization constant, the less likely the compound is likely to ionize. Okay, so this is a weak, actually this is a conjugate acid, not conjugate base. This is conjugate acid. So this is a very weak acid, very weak, because the Ka is very low. Okay, so which means that sodium acetate is a weak base. So to find the pH of this 0.1 molar solution sodium acetate, we have to use ice charts: initial concentration, changing concentration, equilibrium concentration. And we will focus on the equilibrium concentration to find what we call Kb. So the strategy is to look for the equilibrium concentrations of the products and reactants. Our interest will be the concentration of OH minus, which we will call X in our ice chart. We will then, after finding the concentration of OH minus, we'll convert it to potential of the base, potential of OH, and then the potential of hydrogen, which is pH, which is what the question wants. Alternatively, after finding the value of X from the equilibrium concentration, which happens to be the concentration of OH minus, we can find the concentration of hydronium and then use it in the pH formula. How will we do that? Here we'll take advantage of this formula. Concentration of the acid multiplied by concentration of the base is always equal to Kw. Kw is 1 times 10 to the power minus 14. These are equations you have to know. This equation, and another one, pH plus pOH equals to 14. You always have a maximum of pH of 14. So that's the strategy. So let's flow. So here is how you solve the problem to calculate the pH of 0.1 molar sodium acetate weak base solution. The first step is to write the equation of reaction. Here is the molecular formula of sodium acetate. That's your sodium acetate. And you add it to water because it's a solution. What happens? There's going to be an equilibrium again because this is a weak base. This weak base cannot deprotonate H2O, so you're less likely to form the products. To predict the product, use a lone pair on oxygen to take away a hydrogen from water, and then the 2 electrons that make the bond are taken to the oxygen. So you're going to end up with COOH. After accepting this hydrogen, which is this, okay, and then you end up with OH minus. The oxygen will have 3 lone pairs after accepting the 2 electrons in the bond. And of course, sodium is just a spectator ion. We don't care much about that. We know that. So that is the equation. And then now we create our ice chart. Record your initial concentration of sodium acetate before the reaction started is 0.1 molar. The concentration of water will be taken to be negligible, and then initially you've not formed any product, and again water does not self-ionize. Why? The ionization constant of water is 1 times 10 to the power minus 14. Remember I told you the lower the ionization constant, the less likely to ionize. So you don't expect H2O to ionize by itself to give you OH minus. So concentration here is 0. So remember, we are creating the ice chart. We are through with the I. So C will be the change in concentration as the reaction goes on. We'll assume the reaction changes by a concentration of X. And in this case, because this is a starting material, the concentration will reduce. We use negative. Water does not self-ionize. And again, acetate cannot ionize the water, so it's negligible change. And then these are products that will change by equal amount X, because the balanced equation has reacting ratio of 1 to 1 to 1. So X, X, X. If this was 2, we'll put 2X here. Then here comes what we really want, equilibrium concentration on the ice chart. So to find the equilibrium concentration, you add this up. So it's 0.1 plus minus X, which turns out to be 0.1 minus X, because positive and negative gives you negative. Again, equilibrium concentration is negligible for water. When the reaction settles, that's what we call equilibrium. Add these up, equilibrium concentration of acetic acid will be X. Add these up, equilibrium concentration of OH minus is X. This is our focus moving forward. It's going to help us to get POH, which will help us to get pH, just like we mentioned in our strategy right here. Okay? So now that we have our ice chart, we are ready to move on. The problem is that the question gives us Ka, which is ionization constant of the acid, to be 1.8 times 10 to the power minus 5. It does not give us Kb. So we need Kb because this is a base. If this was an acid, we'll use a Ka directly. We know Ka times Kb must be equal to Kw, ionization of water, which is 1.0 times 10 to the power minus 14. So obviously, to find Kb, it will be Kw over Ka, which is 1.0 times 10 to the power negative 14, divided by the Ka given in the question. If you've forgotten, the Ka is right there. It's given in the question, is this one right here. So we need Kb, and Kb will help us to get the value of X, either by quadratic or simplified expression. So Kb turns out to be equal to, if you do the math correctly, Kb will be 5.6 times 10 to the power negative 10. So we know now that Kb is 5.6 times 10 to the power minus 10, and this is equal to product of concentration of products divided by the product of concentration of reactants. If you go back to your reaction, you will notice that your equation has these reactants in equilibrium with these products. Okay, so what are our products? Acetic acid and OH minus. So we'll have to multiply the concentration of acetic acid by the concentration of the base, divided by the concentration of sodium acetate, multiplied by the concentration of H2O, which according to our equilibrium concentrations are these values. We need that, and that. So you can obviously see these two concentrations. Let me just use arrows at those guys. So it's X times X divided by concentration of sodium acetate at equilibrium is this expression minus X. The concentration of water, which is a liquid, is taken to be 1. So So in other words, this will be x squared divided by 0.1 minus x. All right. So let's continue. So KB equals to x squared divided by 0.1 minus x. And it happens to be equal to this number here because you calculated it. Okay. So now, once we have our KB, the expression for KB, we are ready to find x. Notice that if you simplify this expression, it's going to give you quadratic equation. And nobody loves quadratic equation. So at this point, we usually try to see if we can simplify to avoid quadratic equation. Can we simplify? To simplify this, there's a test. Test to ignore x in denominator. Our denominator is 0.1 minus x. So the test is given by this. So because we are talking about the base, sodium acetate, so it's gonna be if the molarity of the base divided by the ionization constant of the base is greater than 100, then we can ignore x in 0.1 minus x denominator. So let's see if this will apply. If this ratio will turn out to be greater than 100, we can ignore this x, and that will make the calculation easy. So remember, in your question, you're given 0.1 molar of sodium acetate. Our Kb was found to be 5.6 times 10 to the power minus 10. Do this math, you'll find that the ratio is 178. 571, which is way greater than 100. So we can safely ignore x in 0.1 minus x. Okay? That saves you a lot of time in the test. So now, this expression right here can be written as x squared over 0.1. We don't ignore the numerator, only the x in the denominator. This must be equal to 5.6 times 10 to the power minus 10. And now you realize that you can easily solve this by just finding square root. Multiply both sides by 0.1 and then find square root of both sides. You get the value of x to be equal to, I did the math earlier, so my x is 7.48 times 10 to the power minus 6. Remember, if you go back to your ice chart, the concentration of OH in our ice chart was x, right? This x. And we need it to find the pH. The question wants us to find the pH, not the pOH. So the concentration of OH minus is 7.48 times 10 to the power minus 6 molar. So there are two ways you can find the pH to finish answering the question. So I'm going to give you method 2 here, and then I'll give you method 1. Okay, so let's first go with method 2. I gave you equations that we'll use in the problem when I started in our strategy. So this was one of the equations. Okay, concentration of acid times concentration of base should be equal to 14. So the concentration of the base, actually what we need is concentration of acid. So the concentration of the acid, which will help us to get the pH, will be equal to 14 over concentration of the base, which of course is 14. Actually, this is not 14. Let me see. Concentration of the acid times concentration of the base should give us Kw, sorry, which is 1.0 times 10 to the power minus 14. That's where my 14 is coming from. So if you want to find concentration of the acid, it's going to be equal to Kw over concentration of a base, which is 1.0 times 10 to the power minus 14, which is ionization of water, what we call Kw, divided by what you got here, 7.48 times 10 to the power minus 6. It turns out that the concentration of the acid will be equal to, let me do the calculation in my calculator. So I have 1 exponent minus 14 divided by 7.48 exponent minus 6. I'm getting 1.34 times 10 to the power minus 9. Then we know that pH is always equals to negative log concentration of the acid, which is negative log 1.34 times 10 to the power minus 9. Your pH will be equal to, okay, let's see, negative log is giving me my pH to be that. So that will be the final answer. That is method 1. For method 2, since you found OH minus concentration, okay, to be equal to 7.48 times 10 to the power minus 6 molar, one can find the pOH, which is negative log of OH minus, which is negative log 7.48 times 10 to the power minus 6, which happens to be equal to, let me see, negative log 7.48 exponent minus 6 is giving me as 5.12. So that's potential of the base. But the question wants pH, not pOH. There's another expression, pOH plus pH must be equal to 14. That's what I was confusing on the other side on method 1. So if you want pH, it's going to be 14 minus pOH, which is 14 minus 5.12 according to your calculator. So 14 minus the answer, I'm still getting the same answer of pH. So either way, either of these two ways, they will give you the two answers. Okay, so the question wanted us to calculate the pH of, so the question wanted us to calculate pH of 0.1 molar solution of sodium acetate. And we found the answer to be 8.87 using ice charts. Alright, see you next time for some more chemistry. Let's see if there's any questions here in our chat. No question.